I've been contributing to Postgres for many years on my own time, but in the last few years I've been working at Second Quadrant and had an opportunity to work on some of the exciting features that Robert outlined in his talk, including logical replication and stuff. But today I'm going to talk about Vacuum. One of the basic problems that every database server needs to address is how to support multiple clients reading from and writing to the same database without interfering with each other, and especially without saying goodbye to performance. This is something that Robert mentioned in his talk as well. There's been a lot of work to speed up concurrent access in Postgres, but the basic design decision of Postgres is to use a technique called multi-version concurrency control to manage concurrent access without heavyweight locking. Now, MVCC is a well-known technique in the database world. It's not unique to Postgres, but this design sets Postgres apart from many other database systems, and it comes with its own trade-offs and operational considerations, foremost of which is the need to periodically vacuum tables to remove dead rows. So this talk is going to explain what that actually means. The basic idea of MVCC is that SQL statements operate on a snapshot of the database as it was at some particular time. So rows in a table have a defined lifetime, which specifies which snapshots they're visible to and which they're not. And Postgres essentially, in effect, allows sessions to pretend that they're the only ones accessing the database at a given time. This behavior is implemented using some simple building blocks, one of which is the lifetime of rows. When you insert a new row into a table, and the transaction that's doing this has committed successfully, a new row is written to the table, and it has an open lifetime. The start is defined as now, and there's no end. When you delete the row correspondingly, and the transaction that deletes the row has committed successfully, that sets the end of the lifetime for that particular row. But it doesn't actually remove the row from physical storage. In fact, the row is left there as it is. The row that you inserted earlier, some new row, it's visible to any snapshot that's taken after the inserting transaction has committed. And correspondingly, after you delete a row and that transaction has committed, it becomes invisible to any snapshot that comes afterwards. The row isn't actually deleted, it's just that its lifetime has ended and transactions know not to look at it. This is analogous to the advice often given to application developers to not delete anything, just mark it invalid and leave it in the database for later analytics or auditing or whatever. It's a system level analog to that behavior. And in this model, update is equivalent to an insert followed by a delete. You insert a new row with the changed values, you leave the old row alone, end its lifetime, and start the lifetime of the new row. The rules for snapshots that come after you've finished committing an update are simple. They don't see the old row, and they do see the new row. So as far as new snapshots are concerned, the database has been changed. But you don't modify the data in place. So existing snapshots can operate on the old row without any conflict. In a sense, transactions know which rows they're supposed to look at, and they leave the others strictly alone. So they don't need to lock the rows that they're operating on. And multiple transactions can cooperate to operate on their own subset of rows without interfering with each other at all. So let's imagine we have a table, right? And the table has some rows. Let's forget about what's in them. There are just a bunch of rows in there. And all running transactions have completed and gone away, and the database is quiet. Now a new transaction comes along and does delete from foo. So all of the rows go away. Now they're still there in the table, but their lifetime is ended. So any new transaction that comes along will see the table as being empty. And that will be the case until somebody inserts new rows, right? And now new transactions will see the table as having 3 rows, but the table on disk will actually have these 7, the 4 that were there before and the 3 that you've inserted right now. The old rows are there, of course, because delete, as I said, doesn't remove them from the table. And those are now dead rows. What that means is that they aren't visible to any transaction that could possibly start now. We don't have any old transactions. The rules for those are kind of complicated. Really interesting, but I won't be talking about that because I'm focusing on vacuum. And these dead rows just take up space at this point. Once they're no longer visible to any running or possible transaction, they just occupy space on disk. And so far, we've seen nothing that, that can remove those rows. So in effect, in Postgres, tables can only grow. You add rows to them, but if you change data or remove data, you start accumulating dead rows. And this is what is called bloat. When you find 4 months after starting to use your shiny new Postgres database that things suddenly look slower, and when you investigate, you find that out of the tuples in your table, out of the rows in your table, very few are alive and a lot are dead and invisible. So this is where vacuum comes in. The primary job of vacuum is to remove dead rows and allow the space to be reused by new tuples that you insert. It also updates table statistics, and I'll go into more detail about that later. It updates the visibility map, which I'm not going to really talk about. And it prevents transaction ID wraparound, which is a failure mode that is specific to MVCC, which I'll touch on later as well. Now, when you vacuum the table, what we want to happen is the 4 dead rows that we had before are marked usable again, so that new rows can be inserted in their place. Now, when you do this, when you vacuum a table with some dead rows at the beginning, your table doesn't actually shrink. The number of pages in your table, which I'll explain again, stays the same. You have extra space in there, but the size of your table on disk doesn't shrink. It will shrink only in the special case when all your dead rows are at the end of the table. Then when you vacuum it, vacuum will helpfully decide that you have a bunch of empty pages and remove them, so your disk file shrinks, and everyone is happy, except that when you add more rows, you'll probably just allocate those pages again. But that's all as intended. Now, before we can discuss the details of how vacuum actually works, we'll need to understand something about how Postgres represents table data on disk. Tables, and in fact, anything that Postgres stores on disk, including indexes and so on, consist of a series of 8 kilobyte pages. I will explain what a page is, but at a high level, a page is just 8 kilobytes of data, and you fill it with tuples, which looks like that. And some of those tuples can be live, some of them are dead, depending on what's actually happening to the table. And for our purposes, a tuple is just a chunk of data. What it contains and how big it is depends on the definition of your table, depends on what columns you have, what types they are, and what data you actually store. But the internal organization of a tuple is, for the purposes of Vacuum, not very interesting. They're just little chunks of data that you store on pages. So we have tables or relations which consist of a series of pages. The pages contain tuples, some live, some dead. As I said, a page is 8 kilobytes. It has a header, which contains some metadata that describes the contents of the page. It may have a footer, depending on what the page actually represents on disk. But for now, we'll ignore that. And then pages have tuples. So the thing with tuple storage on a page is that it starts at the end. Tuples are stored backwards from the end of the 8 kilobyte page, and you keep adding them on as you go. Now, in this particular diagram, it looks like the tuples are all the same size, but they don't need to be. It depends, as I said, on what you store in them. So you can have tuples that are really tiny and ones that are bigger for the same table, depending on what data you actually insert into the row. So you need a way to find where each tuple actually is on the page, because you can't assume that they're the same size. So you have pointers to each tuple, the beginning of each tuple. So the data isn't actually stored backwards. It's just you're stacking up the tuples backwards on the page. But the tuple starts where the pointer is, and then when you add more tuples, you have more pointers. The pointers are all the same size. So you can start after the header of the page, and you can find the third tuple by looking at where the third pointer is currently pointing. At the end, please. Yeah, there's time, lots of time for that. Okay, so we have pages which contain line pointers and tuples. Now, both line pointers and tuples have a bit of internal bookkeeping state, but we'll look at that in more detail later. So we're almost ready to talk about how Vacuum actually works, but there's a complication. Now, in physics, you can say things like, we assume that friction is negligible, and suddenly your equations become a lot simpler and people enjoy your talk a lot more. But I'm not a physicist, and I suspect I can't get away with saying we assume that indexes are negligible. So we need to look at what an index looks like. So indexes are stored on disk, and therefore they use the same page abstraction of 8 kilobyte chunks that tables do. But their actual layout depends on the type of the index. The most common being B-tree indexes, but there are other types like block range indexes, which Robert mentioned, which are new in 9.5 and developed by my colleague. And the fundamental underlying mechanism by which an index works is that it references tuples in a relation or a table or a heap all of which are terms used in Postgres, by their position within a particular page. So the seated of a particular row is, it's a sort of pointer to that row, which says which page it lives on within the relation. And when it says item, what that means is the index of the line pointer that points to that particular row. So you identify the page, and then you identify which line pointer you're interested in, and that uniquely identifies a tuple within a table. So really, despite the fact that there are many different kinds of indexes, all you really need to keep in mind when you're thinking about an index table is that you have some data structure that has references to the tuples that are stored in your relation. And that looks kind of like this. Now, indexes, yeah, so you can see that the entries in your index off to the right point to line pointers rather than directly at the tuples. They could point directly at the tuples, but that means that you can't move tuples around on a page and still have their seateds remain the same. But with this two-level access, you can actually move the tuple, change the line pointer, but keep the line pointer in the same place. So you can do a bit of internal reorganization to remove fragmentation and stuff. We'll be looking at that in more detail. So here I'm creating a simple table with 2 columns. The table has one primary key index because, well, why not? And when I create the table and before I try to insert any data into it, the disk file that corresponds to the table, and I'll explain how we found that, is empty. It's a 0-byte file, and it will stay that way until I actually insert some rows, such as the one I'm inserting here, right? So now you can see that the file on disk is 8192 bytes long. So I inserted one row. That row happened to fit, well, it's a small row, and we needed one page to store that. So it's created that one page. It has one tuple on it, and therefore one line pointer. Now, if I look at PG class, which is an internal catalog table that contains an entry for every entity that we create in the database. So I ask PG class about a table whose name is foo, or actually a relation whose name is foo, because PG class also applies to indexes and other things. And here is what I get. It's a bunch of fields describing what Postgres knows about that particular table. Most of them are not relevant for our purposes, but look at rel pages and rel tuples, which are underlined here. As far as PG class is concerned, right now the table has 0 pages and 0 tuples, which we know isn't true because we just inserted some data into it. So we know it's 8192 bytes on disk, and therefore it has 1 page. So the problem here is that PG class isn't kept up to date by the system itself as it changes data. That would be far too expensive. So the job is done by the analyze command, which, if we run, we can see that it scans the table and updates its rel pages and rel tuples values. In this case, you can see that the table has 1 page and 1 tuple. That value isn't always exact, and we'll look at why that is later in the talk. Now we insert a bunch of new rows into the table. You can see there are 2 strings of different lengths, and then a whole bunch of strings of the same length, which is far too many tuples to fit on one page in this case. So when we run analyze and look at PG class again, it tells us that our relation now has 55 pages and 10,000 tuples. Those are both exact values, which we know because that's how we set it up. And now if we look at the file on disk, which, sorry, I said I'd show you how that's done, but if you look here, the rel file node field in PG class tells you the OID of the table, and inside your PG data directory, the directory base, and then a subdirectory, which is the OID of your database, and a file which is the named for the OID of the relation. Yeah. So here we have that file, which is 450560 bytes long, which is 55 pages exactly. So the file will only ever grow or shrink in 8 KB chunks because the file has no existence except as an array of pages. So now we look at what's actually on one of the pages. In this case, page 0, which is the first page in the relation. And to do this, I'm using a contrib module called page inspect, which is really useful to poke around things like this. And essentially what I'm doing is calling get raw page on the table. I specify a page number, which is 0 in this case, and then ask for a description of the header field on that page, which is the blue blob at the start that I said contained metadata. So it has a bunch of fields. For example, here you can see checksum is 0, which just means that I didn't have checksums enabled for this test. And there are pointers like lower and upper and special, which we'll see in more detail later. Well, okay, not very much later. So lower and upper here correspond to the end of the line pointer array and the beginning of the last tuple on the page, tuple n here. So this is a direct quote from storage/buffpage.h in the Postgres source. Beautiful ASCII art to describe page layout. And it's essentially the same diagram that I had earlier. Fixed size line pointer array, variable sized tuples stacked up from the end of each page. And as the comment says, a page is full when there's no space between PD lower and PD upper on the page to store another line pointer or tuple, or the pair thereof. Now, after we look at the header, which is just the first page header data field there, we use another function in the page inspect module called heap page items, which is actually printing out the array of line pointers on the page. Now, I inserted 10,000 tuples into my relation, so the page is full, right? It moved on to insert stuff in the second page after it finished filling the first page. So I actually have a whole bunch of line pointers there, but I'm just looking at the first 10. You can see here that the first tuple, which is LP1 here, it starts at offset 8152 in the page. So it's 40 bytes long, which is the third LP len field. And it has a seated of 0, 1, which means page 0 and tuple 1, or line pointer 1. The fields that have fallen off the end of the slide aren't particularly interesting. There are only 2 of them anyway. So this shows us the first 10 line pointers, and in this case the first 10 tuples, because the line pointers point directly in order at each of the tuples. Nothing interesting has happened to this table yet. It's just a bunch of tuples that we added. And correspondingly, if we look at the index page using the bt page items function in page inspect, and again look at just the first 10 rows. Now, I won't go into the details of how a B-tree index is actually organized on disk, but you can see here that it points to particular tuples by their seated. You can see 0, 1, 0, 2, 0, 3, and so on. And as it happens, it has a copy of the data from the tuple, which is used for some optimizations. We can pretend it isn't there. But in this case, the index is a primary key index. It's an index on foo.id. And so it has a copy of that, just in case it turns out useful. Right, so let's delete a single row from the table. And then look at what items there are on the page. This is what it looked like before. One line pointer pointing at 8152, 40 bytes long. Then I delete the row, and that particular row has txmax now set to 665, where it was 0 before. txmin and txmax are the fields on tuples in a page which define the lifetime of that tuple according to MVCC rules. xmin says I am alive, and xmax says I'm dead. Any transactions that have an xid larger than xmax will not see that row, or knows not to look at that row when it's operating on stuff. So we've deleted one tuple, and we've seen that the tuple is still there. It's still line pointer 1, but we've just set it as being invisible to snapshots after the delete. So we delete some more rows. And again, this is what it looked like before. We have one dead tuple, and when we delete 2 more rows, something interesting happens, which is that the 2 rows we just deleted, 2 and 3, they have their txmax set. But what happened to the first line pointer? It's suddenly no longer pointing at 8152. It's just gone. Now, this is kind of like Vacuum, but it's implemented slightly differently. When you are accessing pages, if conditions are right, if it wouldn't interfere too much with performance, and if it's actually worth defragmenting the page will be defragmented on the fly. It's as if you were running Vacuum, but it isn't actually Vacuum, it's a different part of the code. But what this means is, as you keep deleting rows and continuing to access the table, to scan the table in some way, whether to delete more rows or to select everything or whatever, it will empty out line pointers that point to tuples that we know are dead. Tuples that there is no question will never be seen by a live transaction again. So here we see that the first 3 line pointers are empty because when we deleted 5, 6, and 7, it took the opportunity to remove a bunch of line pointers. So now those line pointers could actually point to new tuples if the system chose. So that brings us finally to Vacuum. You can vacuum a table by using the vacuum command or the vacuum db command line tool, which everyone has forgotten now that we have auto vacuum. And of course there is auto vacuum, which is now enabled by default and knows how to vacuum stuff without overloading your system all the time, or so one hopes. And then we have this opportunistic vacuum behavior that defragments pages as it goes, but isn't actually vacuum. It's implemented in backend access heap prune heap.c in a function called heap page prune opt. where the opt stands for optional, but might as well stand for opportunistic. And when you scan the table, it tries to decide if it's worth defragmenting, and if it isn't, if the page isn't prunable, it just returns. So it does any work only when it judges that it wouldn't, it's worth doing and wouldn't hurt anything. Yeah. So that's yeah, okay. So yeah, I'll go a bit faster. This is what we want to happen after a page is pruned opportunistically, right? So we have two line pointers pointing to two live tuples, but the space in between has gone gray and is in principle available for the storage of new tuples. Yeah. And when we do that and then look at the index, so this pruning is happening opportunistically, and it doesn't change the index at all. You can see that the index still refers to the CTIDs that were there to begin with. And yeah, so that's what it looks like. The index still points to the line pointers that are dead, even though they don't point to tuples in turn. So if you scan the index and try to find rows, you'll see that there's an index entry pointing to a dead line pointer, and then you know to ignore it. So if we keep deleting rows, we keep cleaning up line pointers as we go along, even if there are line pointers in the middle, such as 4 here, which still point to live tuples. Yeah, so we delete a bunch of rows, and then we insert some rows. And what do we expect to happen? I'm looking for tuples that have used the space that was freed. But in fact, nothing has changed. And that's because I forgot that my table was 55 pages long. And so it's actually inserted them at the end of the last page, which is sensible enough. So if I delete all of the pages between, well, 17 and 10,000, then I just have the few tuples at the start and the few at the end that I inserted by hand just now, right? Then if I vacuum, the number of pages still doesn't shrink. This is because all the holes are in the middle, and there's no opportunity to shrink the table very much. So if I vacuum full, what that does is it will reorder entries between pages, which is something that opportunistic heap pruning never does. It operates within one page. But vacuum full, which is different code, knows how to, obviously in a heavyweight locked operation, reorder items between pages. And so we end up with a table that has just 7 tuples in one page. The stuff I didn't delete. And that's what the fully vacuumed heap looks like. Just 7 line pointers and everything stacked up neatly on the page starting from the end. Now, I've pretty much run out of time, so I will skip to the end. Please feel free to ask me about any of this stuff later in the day. 5 minutes, yeah, okay. So the last thing that Vacuum does, which, as I said, was specific to MVCC, is preventing transaction ID wraparound. So I can't say it any better than the Postgres documentation itself says. XIDs are 32-bit fields, so after 4 billion transactions, they will wrap around to 0. The system depends on being able to say so-and-so XID is bigger than this or smaller than this. That's how it determines row visibility. So if it wraps around to 0, all your transactions become magically invisible, which ruins people's day. Vacuum can prevent this by rewriting the table in a special way. This is something that, again, Robert mentioned. In 9.6, we're hoping to have a vacuum freeze map, which will prevent ruining people's day by forcing them an entire enormous table just to freeze rows that are from really old transactions. So that's not actually been committed yet, but there's work going on, and I hope it will be in 9.6. It would be a major win because really the anti-wraparound vacuum goes through the entire table. It is forced to go through the entire table to rewrite XIDs to the frozen XID as it describes. And you can't avoid it, because if you do incur wraparound, then yeah, all your data becomes invisible, and that's never any fun. I have a few minutes for questions if anyone has any.
Questions, anybody?
It's regarding auto vacuum.
Okay.
So auto vacuum anyway we have available. So how good that auto vacuum you want me to rely?
Yeah, please.
Okay. The auto vacuum which we enable, right?
Yes.
So is it good or bad? That's what my question is.
It's mostly good. It's sometimes bad, but you have to be doing really special case stuff these days to make it bad. Keep it enabled.
Okay.
Put two parts to my question. One, the transaction ID wraparound that when vacuum forces a vacuum during a transaction ID wraparound, is that a stop the world kind of a vacuum?
Is that a, sorry, is that
stop
a
the world kind of, so let's say you have a very high transaction OLTP database.
Yeah.
And you realize that the transaction ID wraparound is happening, and it forces a vacuum as well.
Yes.
Is that a stop the world, everything goes for a stop kind of?
Yes. In fact, Postgres will completely refuse to process commands if you reach within a particular threshold of transaction ID wraparound, because it's such a catastrophic thing to happen to your database that it just says,
basically
sorry.
It's a stop. If
yes.
It's a stop.
If it happens, then you have to start your database in single user mode and run Vacuum as a system administrator until it's done.
The other small part is, does Vacuum process very large tables in parts, or is it already there, or it's not there at all? In sense that can you try to do batches rather than doing it in a single go entire run?
Not explicitly, but the way auto vacuum is written. So if you run manual vacuum, it will run until it's finished. It has no concept of working in chunks. But auto vacuum tries to do that, and it's not something you can do explicitly. You don't have very much control over where you stop and start and things like that. But that's actually something that I'm working on making better. I'm hoping to make the entire vacuuming process more controllable. So that's something that maybe we can look forward to in a new Postgres.
Sajay Kumar. I just want to know what will happen to the indexes when we run a vacuum full command.
Sorry, what will happen to?
The indexes, whether it will be rebuilt or we have to
yes, actually there's a slide that shows what happens when you vacuum full, yeah, well, sort of. But when you run vacuum, it will first vacuum all of your indexes. You run vacuum on one table, it'll find all of the indexes that point to that table, vacuum the indexes one by one, and so you can actually see from the vacuum verbose output that it processes the indexes right at the start. Then it processes the heap, where it says foo, found 2 removable, 5 non-removable row version. That's it processing the heap. Everything above that is rewriting indexes. So yes, vacuum full will do that. Even normal vacuum will do that. Even auto vacuum will do that.
Hi, I have a very naive question. When you talked about the design of the page,
yep.
You said it's 8192 bytes.
Yep.
It kind of smells of dependency on mbuf-like structures, which are typically seen in network packets. So, is there some kind of a rule or a thought or a principle that went in when we decided it's 8192 bytes? Why not 16? Why not 4? Why 8? 8192?
I don't know the answer to that. It's historical reasons. Usually hardware has, common hardware has 4 KB pages, and at some point, I guess 8192 looked like the right answer. You can probably change that, but it's stupid and there's no need to do it. 8192 works well for now.
If you look at the diagram that you had kind of
Yeah. Let's see.
Yeah.
Okay, that one.
So I think
Further back?
Yeah.
This one?
So in this case, you have a header and you have a footer. So you effectively mark the range, and then you're kind of appending it just towards the end.
Yeah.
So what's the rationale? Does it make pointer arithmetic easy? Is that the reason you're doing it? Because see, I'm from a networking background. I see an overflow. So I would eventually move to a page and anyway have to move out. So I was just thinking, what's the rationale putting at the end and then doing a back calculation of the pointer?
The rationale is simply that you can do opportunistic reorganization of the page as you go. If you started with a fixed index where the tuples start, let's say you started tuples at 4,000 bytes from the beginning, then the number of line pointers and the number of tuples on the page that you could fit on a page becomes fixed. You can't have more line pointers than 4,000 minus the end of the header. This way, it accommodates tuples of different sizes, and the line pointer array and the tuple array can just grow towards each other. And you don't actually have a limit on how many items you can fit, but you can reorganize the items on the page, which is a major, major win. It's fundamental to the operation of how Postgres deals with pages.
I guess the only thing that appears to me is that as long as the tuples fit into the 8192, this kind of works. The moment you have overflow, then you're moving on to 8192.
Right, that's one of the slides I skipped.